In this video, we're going to have a look at how we can expand trigonometry by also using it on the Cartesian plane. Up to now in trigonometry, we worked with right-angled triangles and measured and determined the angle sizes and side lengths. Now we're going to add that triangle to the Cartesian plane. The Cartesian plane, or system of axes, has an x-axis or number line that is horizontal and a y-axis or number line that is vertical. The point where they intersect is called the origin, and that is the coordinate 0, 0. Now we're also going to measure the angles on the Cartesian plane. When measuring angles on this plane, we start on the positive x-axis and measure anti-clockwise. This means that the positive x-axis is 0 degrees, and as you measure anti-clockwise at the top, you will measure 90 degrees. Continuing further, we have a straight angle of 180 degrees, and then moving down to the bottom, we have 270 degrees, and right around means we've measured 360 degrees. We can now, on the system of axes, choose a coordinate and from there draw a right-angled triangle from the origin to the x-axis. From here, we can now measure the angle in the triangle anti-clockwise, and we can also use the coordinates to determine the side lengths. This coordinate consists of an x and a y value. The x value of 3 shows us that the point y goes up to 3 on the x-axis, which means the adjacent side is 3 units. The y value shows us how high up this point is on the y-axis, which in reality shows us the length of the opposite side. Using the theorem of Pythagoras, we can also determine the hypotenuse, and in this case, the hypotenuse will be 5 units. We can now plot a point anywhere on the system of axes, and from there draw a right-angled triangle. I'm going to show a few examples where I would like to keep the hypotenuse the same length of 5 that we calculated. To do that, I'm going to draw a circle on the system of axes with h on the circumference of the circle. Now I know that the hypotenuse is also the radius of this circle. If I now plot a point anywhere on this circumference of the circle, I know that the hypotenuse will be a length of 5. So for example, if I choose a point I know that the right-angled triangle that I form, looking from the origin, will have an opposite side length of 4 and an adjacent side length, which is the x value, of -3. Similarly, when I look at the point J, I can draw my right-angled triangle, and looking from the origin, I know that my adjacent side again is -3 and my opposite side will be -4. And looking at a last point, K, which is 3 minus 4, I know that my hypotenuse for all of these will be 5, the radius of the circle. The adjacent side from the origin will be 3, and the opposite side will be -4. From this, you can now see that the hypotenuse, which is the radius of the circle, will always be a positive value, but the sign of the adjacent and opposite sides will be determined by where on the system of axes the point lies. The system of axes is divided into 4 parts. We name these parts starting at the top right with the first quadrant, top left is the second quadrant, then at the bottom left we have our third quadrant and our fourth quadrant. In the first quadrant, the x value as well as the y value will be positive, and as mentioned, the hypotenuse is always positive. In the second quadrant, the x value or adjacent side is negative, the y value is still positive, and the hypotenuse is also positive. In the third quadrant, we still have a negative x value. The y value is now also negative, but the hypotenuse stays positive. Lastly, in the fourth quadrant, our x value is now a positive value again. the y value is still a negative value and the hypotenuse stays positive. Because the sides can now be positive or negative, it means the trig ratios can also be positive or negative. The sin ratio, which is defined as the opposite over hypotenuse, can now also be written in terms of the system of axes as the y value over the hypotenuse or radius. The cos ratio is defined as adjacent over hypotenuse, or then x over the radius, and tan is defined as the opposite over adjacent, or then the y over the x value. If we now focus on the first quadrant, you can see that all the side lengths are positive. This means that all the ratios will be positive in the first quadrant. In the second quadrant, the sin ratio, which is opposite over hypotenuse, will be positive. The cos ratio is the adjacent side over the hypotenuse, and this will become a negative ratio. And the tan ratio will be the opposite over the adjacent, and a plus divided by a minus will give us a negative ratio. Moving on to the third quadrant, the sin ratio will be the negative opposite side divided by the positive hypotenuse, and that will give us a negative ratio. The cos ratio is the negative adjacent side divided by the positive hypotenuse, and that will also give us a negative ratio. And the tan ratio in the third quadrant will be a negative opposite side divided by a negative adjacent side, and a minus divided by a minus will give us a positive ratio. In the fourth quadrant, the opposite side is negative and the hypotenuse positive, and that will form a negative sin ratio. For the cos ratio, we have a positive adjacent as well as a positive hypotenuse, forming a positive ratio. And finally, for tan, we have the negative opposite divided by the positive adjacent side to get a negative ratio. To make a quick summary of this, we can say that in the first quadrant, all the trig ratios will be positive. In the second quadrant, only the sin ratio is positive. Moving to our third quadrant, only the tan ratio is positive. And in our fourth quadrant, only the cos ratio is positive. There are many different ways to easily remember which trig ratio is positive in which quadrant. I always use the sentence, all stations to Cape Town. In the next video, we are going to have a look at how we can use this new knowledge in calculations.